Hello, this is Math 2231, coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is Improper Integrals. Let's begin by way of introduction to recall the fundamental theorem of calculus. So suppose lowercase f of x is a continuous function on interval ab, and also suppose that capital F of x is an antiderivative of lowercase f of x. Then the definite integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a. And that was one of our fundamental theorems. Now, we can think about, and mathematicians would think about, what happens if we relax some of these conditions. In the lecture on numerical integration, we saw some ways to approximately address the area problem when we could not find an antiderivative. And those were Simpson's rule and the trapezoidal rule. Today we're going to deal with the others, or in this lecture we're going to deal with the others anyway, continuity and the finite interval. Now, if you are continuous on a finite interval, the integrals are considered proper integrals, wherein continuity on a finite interval is assumed. In this part of the lecture, we will relax the constraint on the finite interval portion. Keep in mind, however, that infinity is not a real number, but rather a limit of real numbers. Let's dive right into an example, and this is evaluate the following integral. So the integral goes from 1 to infinity, 1 over x squared dx, and you're being asked to evaluate this. I'm going to move directly to this solution. I'll ask you to do things later. So here's what we do. We define a sub t to be the integral from 1 to t of 1 over x squared dx. And we're taking t to be some arbitrary number out here. So it's there, or it's way out here. So when we do that, this is x to the minus 2, so that's going to be minus 1 over x. We evaluate it at these points. When we put t in there, we get minus 1 over t. This minus sign is from the fundamental theorem of well, we do another minus sign from the fundamental theorem of calculus, but it's a minus when we put 1 in there, so that makes a positive 1. So you see what we have is that this is 1 minus 1 over t. But what happens when we take the limit, and this is what we define to be the area, the limit as t goes to infinity of a sub t. What's the limit of this? And as t goes to infinity, this part becomes smaller and smaller, so this limit is 1. And so that is the answer to the problem, and here's how you would write it. So this is defined to be the limit as t goes to infinity. We do the integration of this up to t, and then we take the limit of our answer as t goes to infinity. Okay, so let's move forward and talk about some definitions here then. We call these integrals convergent if the associated limit exists and is a finite number. And that means I'm saying it is not plus or minus infinity. And we call it divergent if the associated limit either doesn't exist or is plus or minus infinity. Okay, so let's talk about how we deal with this, and there are basically three cases. So if the integral from a to t, f of x dx exists for every t greater than that, then this is the limit as t goes to infinity of the definite integral here, provided the limit exists and is finite. If the integral from t to b, f of x dx exists for every t less than b, then this, and notice I'm using minus infinity here now up to b, f of x dx is equal to the limit as t tends to minus infinity f of x dx, provided the limit exists and is finite. And now we deal with a even broader case. If the integral from minus infinity to c of f of x dx and the integral from c to infinity f of x dx are both convergent, then the integral from minus infinity to infinity f of x dx is equal to the sum of those two, and c can be any number. A lot of times we are wise in picking what the number is. Note as well that this requires both of the integrals to be convergent in order for this integral to also be convergent. If either of the two integrals is divergent, then so is the integral that we started with. Well, let's do another problem then, and I am going to ask you to do this one. So determine if the following integral is convergent or divergent, and if it's convergent, find its value. So we have the integral from 1 to infinity of 1 over x dx. You know what to do. Let's see how you did. Well, when you integrate from 1 to t, 1 over x dx, you get that that's going to be the natural logarithm of x at t and 1, and we're going to take the limit as t tends to infinity. And so that's going to be the limit as t tends to infinity of the natural logarithm of t minus natural logarithm of 1. Now, natural logarithm of 1 we know to be 0, so this is really just talking about the limit as t tends to infinity of the natural logarithm of t. Now, I'm claiming that that is infinity, and we will talk about that, and the integral is divergent. So we'll go back and talk just a little more about that. But you can see, in comparison to what we did before, the blue curve actually is above, so you might say, oh, that area could be more, because for most of the, in fact, for the entire time we're looking at, that is, the blue curve is above. And when we look at the natural logarithm, the red curve, we see that it grows, but it's growing very slowly. But when we look at this derivative, that's the 1 over x, we see that it is always positive, meaning it's always decreasing, albeit very slowly. So it really does continue to grow and continue to go towards infinity. Now, this raises a mathematical question. We saw that the integral from 1 to infinity of 1 over x squared converged. And we saw that the integral from 1 to infinity of 1 over x dx diverged. So the question could be raised, when does the integral converge? For what values of p, and what is the value that we have? That's a great mathematical question, and one that I think you will want to work on. So you know what to do, and we'll revisit this when we return in 41.1.